Today, we want to do a quick review of our double and triple integrals. We've had multiple coordinate systems. So in the category of double integrals, we can set up a double integral in rectangular coordinates or polar coordinates. In the case of a triple integral, since we have three choices, we have rectangular, cylindrical, and spherical coordinates. When we start using angles as one of our coordinates, we start having to have these extra factors in our double and triple integrals. For our double integral in polar coordinates, we need that extra factor of r. For our triple integral in cylindrical coordinates, we need that extra factor of r. And for a triple integral in spherical coordinates, we need this extra factor of rho squared sine phi, which is a rho and a rho sine phi. It's like two extra factors. What we want to understand is why we need these extra factors. Then we want to think about where these extra factors come from. Remember, the reason that we need these extra factors is that we're thinking of dA as an area, which is a distance times distance, and dV as a volume. That's a distance times a distance times a distance. And the problem that we run into is that one of the variables that we're using is not distance, it represents an angle. D theta is an angle. R is a factor that turns d theta into a distance by using the arc length. It's just how far we are from the pole that makes the arc length bigger. We still have to remember how integration thinking goes. Now, dA is supposed to be an area where we're just doing length times width. Our d theta is a little bit curvy. So our area is not going to exactly just be length times width. But if we make theta, d theta small enough, then it'll be close to just a rectangle. The smaller we make the sides, the closer our sector is to a rectangle. In the case of triple integrals, the r in the cylindrical coordinates is the same r that we have in polar coordinates. But in the spherical coordinates, we needed two factors because two of our variables are expressed as angles. D theta and d phi. D phi requires an extra factor of rho to get an arc, to use the arc length. And d theta, we don't have r anymore. We had to calculate r as rho times the sine of phi. And that's the extra factor that turns theta, d theta, into a length. So we want to understand why we need these extra factors and where do these extra factors come from. We also want to think about the entire process of integration and how integration works. We set the problems up as dA and dV, where dA is some area and dV is some volume. And so we're kind of setting up X, Y, and Z to all represent distance. So meters times meters times meters. But it doesn't have to be that way. X, Y, and Z can represent anything that they want. Whatever units you're using to represent X, Y, and Z, the product of those units will tell you what dV represents. So it could be, they could be a lot of different things. Any questions? These are just the most convenient. This all goes back to when we first started talking about area under the curve, and how the only application of integration we really need is area, because area is multiplication, length times width. And that's convenient for us to use because I said, let's do this to find the area. And the only area we need is length times width. Turns out that's the only application we need. If our two factors are something else, instead of length and width, we have rate times time, then our integral will tell us distance. If we got force and distance, then our integral will tell us work. If we got pressure times area, that will tell us force. Whatever product we have, that's what we're calculating. I don't even know how it would work, but if you have we know that voltage is current multiplied by resistance. So if you had a constant current at a constant resistance, all you have to do is multiply to find the voltage. But what's the change in voltage if your current varies over the resistance? Then we have to integrate. I don't even know what that would represent. I bailed on electrical engineering kind of early on in my scholastic career, so I could do math. I'm going, you mean math? The lab just takes place in your head. You think about stuff. Sign me up. Also, in my chemistry class, I'm like, oh, wait a second, you want less than 5% error? All right. So very suspiciously, my next lab had exactly 5% error. And it was pointed out, it's like, oh, wow, you got exactly 5% error. And that communicates to me, it's like, oh, you don't want that much precision. So the next lab had 4.87% error. And so I just decided that the error was going to be decided by rolling a 4-sided die and a percent die, and then flipping your coin. Flipping your coin to get over and under. The D4 will tell me between 1 and 4 the units, and the percent die would tell me the percent. And I had the cleanest lab equipment in the entire room. Me and my lab partner, the cleanest lab equipment in the entire lab. I think the statute of limitations passed on flunking me now in chemistry because that was like in 1990. So that school kicked me out anyway. So, but not for making up chemistry. Any questions? Don't fake your chemistry lab. That was shitty behavior on my part, but I was stupid. You could tell I was going to be stupid because I was like 19. That's pretty much all the evidence. Is this person going to do dumb stuff? How old are they? 19. Yes. They had really good grades in high school. Yeah. Still going to do dumb stuff. Any questions? Comments? Snide remarks? All right, we're going to spend some time, we're going to spend next week kind of catching up on all of the stuff up through integrals. You may have noticed there is some stuff in chapter 14 that turned into chapter 15 that we haven't gone back to yet. So we're going to be cleaning some stuff up. But the next big thing for week 10, we're going to be jumping into vector calculus. And I kind of want to start vector calculus today, not in detail, just in thought. So when we think about integration, integration is multiplication, but one of the factors is continuously variable. What we get out of this is that applications of multiplication are applications of integration. Applications of multiplication, anywhere we're using multiplication, if we can take one of the factors in your multiplication, one of the factors in your product can be, if one of those factors can be made continuously variable, you can create an integration problem. So this means applications of multiplication can give us applications of integration. And that goes back to the beginning where we were thinking about what integration could be used. Integration is multiplication, but one of the factors is continuously variable. We know how to deal with this. We take care of the continuously variable by assuming our function is constant for some small changes. We assume that that continuously variable factor is constant for small changes in the other variable. That's how we framed integration. We take care of that continuously variable part by making what the continuously variable factor constant for small changes in the other factor. So then we have vector calculus. Since I said vector calculus and multiplication, we need to start thinking about the multiplication that can show up when we're dealing with vectors. So if we have vectors, we have a couple kinds of vector multiplication. So if I say vector calculus, you should start thinking, oh, integration, but now with vector multiplication. And what do we have for vector multiplication? Dot product and cross product. Yes. Sometimes you might have to be doing some weird stuff to make one of your factors continuously variable. Like I do not know in the multiplication voltage is current times resistance, how you make current a continuously variable function of resistance or resistance continuously variable function of current. I do not have that knowledge. Electricity kind of bothers me because it's dangerous. So I don't want to mess with electricity. That's dangerous. So I don't know how, but there might be a way. Electrical engineers, don't at me. I'm not an electrical engineer. So what we're going to start looking at is integration and differentiation, but now with vectors. What kind of vectors do we have? Or what kind of vector multiplication do we have? We have dot product and cross product. To figure out where we can apply integration to dot product and cross product, we have to make sure that we understand what dot product represents. We have to make sure that we can interpret dot product and cross products. We got to think, what's dot product for? In the same way, when we're thinking about what we can do with integration, just plain integration, what's multiplication for? Here's one, length times width. Distance is equal to rate times time. And those are your classic examples of engineering calculus integration problem. So what are we going to talk? What does dot product tell us? On one hand, it tells us how much of one vector is going in the direction of the other vector. Then that gets multiplied by the length of the other vector. But u dot v is going to be uv the magnitude of u times the magnitude of v times the cosine of the angle between them. So it's giving us, if we make v a unit vector, we're getting the v component of u. Or if we find u dot v and just divide by the length of v, we're getting the v component of u. So if we take u dot v and divide by the length of v, we're getting how much of u is going in the v direction. How much of u is, one way we can think of this is how much of u is cooperating with v. Or if theta is greater than 90 degrees, how much is u fighting against the direction of v? So in vector calculus, the classic example is no longer going to be length times area is equal to length times width, or distance is equal to rate times time. Our canonical example is going to be work is force dot distance. So if I'm walking along trying to drag a train at this angle of theta, and I don't want the train to run over, that's why I'm standing off to the side. Not all the force that I'm using to pull along the direction of v is being applied in the direction of v. I want to know how much of my force u is pulling in the direction of v. And that's given by the dot product. Work is equal to force times distance in single variable calculus because there's only one direction. Well, once we have more than one direction, work is equal to force dot distance. This is going to be our classic example. We need to start thinking of the dot product of how much of one vector is going in the direction of the other vector. U dot v divided by magnitude of v will give us the v component of u. How much of u is pulling in the v direction. This is just one dot product that we could think of. But we always need something kind of latch onto. Here's one thing that we could do with two vectors. So at a point, we got vectors all over the place. We got two vectors, and maybe there's a path for one vector. We can see what's going on as we carve a path through a bunch of vectors. Any questions? Is everybody okay? All right, that's what we wanted to do. Just kind of take a step back, think about our double and triple integrals in different kinds of coordinates, get a little bit of a preview of where things are going when we get to vector calculus. We'll save that for week 10. All right, so that's going to do it for today. That's going to do it for this week. Grab a cookie on your way out. Everybody have a good weekend. I'll be in my office tomorrow, 9 to 11 like normal. Probably only on Zoom. Tomorrow's pretty sketchy, so probably only on Zoom. So send me an email if you'd like to meet, and I'll be on Zoom. That's it for this week. I will see you on Monday. Grab a cookie. Have a nice weekend, and thanks for playing.